Hey guys, so I've been getting a few requests or a handful of requests to try to do this in 3D, so I wanted to try to do this out myself using the method I showed in that other video, and I get a mesh that looks something like this, but now in 3D. So this at first looked pretty good to me, I thought uh it looked pretty good all around. Uh I wasn't doing anything too crazy. I did I had to think about all of these edge sizings. But I want to show you guys that this, for me, did not work. I don't know why. When I throw it into the Fluent solver, I get divergence detected when I try to initialize it, and it simply just doesn't work. So today I want to try to show a different way to mesh and run a 3D simulation that uses wall functions or the K-Epsilon model. It's a great way that reduces computational demand. And it is much simpler, something that doesn't take time to learn how to do these 3D edge sizings because this took me time to think about it. And you don't really need to think about the topology because we're going to be using inflation layers. So going back, oh, this is my Airfoil plotter. I'm using a remote desktop to use an academic license, a research license, and so just to preface it, 3D simulations take much more cells. You're not going to be able to run a good 3D simulation probably under 500,000, or even I'd say probably over 1 million for most 3D simulations, unless it's very small. But just talking about y plus really quickly, I think it's good to understand what y plus is. Y plus, as I mentioned, is the non-dimensional first layer height, and essentially y plus correlates to u plus, which basically correlates to velocity. So if you guys remember, during in the boundary layer, the velocity profile or the velocity profile is rapidly changing. So you want your first layer height to essentially obey. You want to be able to know from that first layer, um, where it is in the viscous sublayer and what laws governs that height. So if you can see here, at small y plus values less than 1, it will govern a different law, or it will be governed by a different expression for the velocity than if it was above 30. This is generally above 30. And so in this region between where it says u plus equals y plus, that's one expression. But above 30, it follows a different expression. So that's why it's important that you're generally either below 1 and it follows one expression, or it's above 30 to maybe 100 where it follows a different expression. These expressions tell you basically what the velocity is and therefore what the shear stresses are. So it's important you're using the correct value and the correct models for given y plus values. If not, you're going to be using, so per se, you're at a y plus greater than 30, but you use a low y plus value model, you're going to be saying that the velocity at that first layer height obeys this expression, when in reality it follows this type of expression. So you're simply going to get the wrong value. So I'm going to use a wall function that has a larger y plus, but it already incorporates this value inside of it. Um, so going back to my remote desktop, not looking at this, yeah, I'm just gonna tell you guys this does not work. Maybe it'll work for you, didn't work for me. I thought I did this meshing just fine. So using that same, where is it? Some of the same setup. I'm gonna vary the depth to show that, it's not just 1 unit depth. Uh, but I'm still gonna use a 2 meter long. Do I say that here? Well, whoops, I used. Alright, I'm just gonna make this. Ooh, should I make this 1? I'll make this 2. Okay, I'm gonna make this 2, and by Reynolds number, to keep the same Reynolds number, I will have to divide this by 2. So, be 44.325. I'm just gonna round down 32. Alright. Um, so I changed this a little bit, increase the length, uh, and so I've been playing around with this already, or not really playing around. I haven't run the simulation that worked perfectly well, so you're gonna have to kind of bear with me as I do this on the fly. Um, yep, just as a reminder, this is gonna take more computational demand. See, like for right now, this happens once in a while. I don't know why. Uh, for me, I kind of gotta. It takes the time for me to have it working. I just close this out. It's basically saying I don't have the proper license since I'm using a particular research license that uses my school's, or my lab's, whatever particular license it uses. So here it works. So in this case, I didn't even use CMesh because uh, I'm actually going to limit myself to how much angle of attack I use because in real world wind tunnels, you're not varying this inlet. In reality, you're keeping, this constant and you vary the angle of attack of your airfoil such that it rotates like about this point it rotates clockwise, something like that. So and in reality these are walls. I could do walls, but I'm just going to set all of these to inlets. So far I imported the curve. You guys should know how to do that. You format the text file. I think I have my text file formatted like this. I did that in the other video. If you don't know how to do that, check that other video. I use a closed edge. That's with these last 2 points. If I didn't have these last 2 points, it would not defaultly close them. uh, I created a surface, and then I created two different surfaces, and you'll find out later this overall surface um, is based on this sketch. I have a first sketch made. This is basically the fluid domain, and this second sketch is what I'm going to make a body sizing. Body sizings are when my mesh, I'm going to have an unstructured mesh coupled with a inflation layers, which are prism layers, aka, or whatever you want to call them. You guys should know what that is. Uh, I'm just gonna say, in addition to that, in this region, I want better sizing than the outside. Basically, you'll see it's really not that super complicated. I kind of just abstractly drew this and said, if I define all the elements in here more, it probably will work well. Uh, so I basically have a bunch of surfaces, but this is in 2D still. And so one thing too is when I created this, it's important to add frozen. So why don't I suppress? So after I suppress, so imagine I just made my airfoil surface. I created the sketch, and I have to add frozen. What the add frozen does is it adds this without combining it with this. It's like in SolidWorks you can add different bodies together or you can merge them. Same thing here. I basically have three different things. And so for I will say there's a unit depth of, let's say, half a meter. All right. Oops. So I have to do that for all three of these actually. First off, I'll just take the first one. Where is extrude? So I say what geometry? I'm gonna have this surface, or I can even click surface body. That should be that one. Direction vector, you need to choose your sketch plane, and it will be normal to it. Unit depth, I will have 0.5. Generate, boom. You can see it's 3D now. 0.5 meters, chord length 2 meters. I don't know what type of theoretical wind tunnel you're trying to use, but this is going to be mine. Then I need to do the same thing with this surface, my second surface. I'm not going to add material, remember. Keep it separate because we're going to do a Boolean operation. Normal to... Alright, so I have two surfaces. Oh, actually, I clicked this one. I didn't mean to click that one. I meant to click the other one, but it doesn't matter what order. I can also click this. Frozen. XY plane normal. Extrude. So I have three bodies. I want to keep this internal bigger one. I will keep that separate. and you'll find out. You'll see later. So then I want to do my Boolean operation. I will subtract target is this big fluid domain. My tool will be my airfoil. Alright, so basically I should only have, and once you kind of create things, you can suppress these line bodies, and you can even suppress the surface bodies. You really just care about the solids. So you have two solids right now. You have, I can hide this internal one. So right now, I basically have, this is my fluid domain. If I hide that, this is the region I'm going to define as a surface body operation. Alright, think this should be okay. This is as a preface, this is kind of a rougher CFD simulation. Like generally, in general, if you want to do the most accurate possible, you should avoid wall functions, and you should try keeping with K omega SST. But as I showed in that Start CCM video, the K omega is the most accurate. Basically, for a two model simulation, K omega is generally the best. Wall functions, you know, they approximate everything. They are wall functions. That's the thing. So yeah, they approximate all of this. When in reality, K omega can solve for this complicated region and then switch to something like this farther away. That's actually what the K omega SST does, is it uses this, it focuses on this, and then it switches to a wall function farther away. Oops. So here's my mesh. Alright, so this is the tricky part. So what I first, yeah, there's really only two operations you need. A body sizing, and you know, I would, should I suppress? Because I want to show this. Yeah, actually, I will delete this. So let's start off with the general mesh. So when you generate your mesh, you start off with your default settings. These settings are applied for the whole thing. So yeah. Good. Actually, I already deleted the connections, but eventually, okay, I'll talk about that in a sec. But basically, from here, I might want to look at first the total element, the overall element size. Uh, I think this is already tweaked, so it might have been much bigger, and I moved it down. This applied to everything, so if I want to change, so statistic-wise, how many elements am I? I'm at pretty little. So yeah, defaultly it was, I guess, 0.4, 0.75, but I just changed it to 0.1 for my max size, and I set my growth rate smaller. Uh, element size, see, like I could make this as small as my max size. Just for demonstration purposes, sure. I'll make this 0.05. So you'll see, oh, max size must be greater or equal to element size. So actually the element size should be, this is the part. There, that's right, because it starts at element size and it grows out to your max size, basically. So in the case that, you know, I set them equal to each other, I'm basically saying it should all be the same place everywhere. So actually, shoot. I will make this 0.01. And I'll make this 0.2. So actually, I think it was using that 0.47 whatever. It was actually using that size. So these are all actually like 0.7 something. So actually, didn't see much of a difference. So it's probably more dictated by max size or element size. Here. You see it's taking longer. It's taking a bit longer because in 3D, you know, you have a whole another dimension. Boom. Everything got half as small. And we're already up at 200,000. So we were at 40,000, now we're at 200,000 just like that. Uh, and yeah, this looks kind of ugly right now. So I have, alright, so I have, why is this geometry should be, actually this might be right. So let me hide this. Oh yeah, yeah, this is fine, this is fine. Yeah, so I say, alright, you know, I have a, let's say I have a base. Right now I'm thinking about the outside. Outside looks fine. First, then I want to create a body sizing. I will do, so you have to click bodies right here. So this selects what your selection part is. Element size. And so it already knows it's a body sizing. Oops. So I'm basically saying in this body, I want a smaller element. So default, which is the outside, is, you know, 0.05. Let me make inside here 0.01. 0.02. And remember, soft makes it like, you know, you're not saying you have to do this. You're saying you kind of can do that. Try your best to do it, essentially. And so as I generate mesh, this will probably take longer. So now I have two bodies. I have this external body, and I have this. Oh, actually, shoot. I think I might be supposed to be doing a sphere's influence. But basically, look, like I have a geometry. I have this region inside is basically more defined. And why does it look so ugly? No idea. That's just how it looks. And so from here, I want to do an inflation layer. So I want to do it on this body. My boundaries, let me hide this. Yeah, my boundaries are these inside part, right? I'm gonna make sure that there's no region here. Actually, yeah, this is smooth, so this should work. Inflation layers, I want, let's just choose 15. Growth rate, I like to limit that. Ideally, you should actually have your last inflation layer equal to the size of the outside. Uh, and you could do that by basic math and first layer thickness. And I should have calculated it right here. So using a 2 reference length, this is supposed to be 44.32. So I want a 30 y plus y. And so for me, it's about 0.27 microns or 0.27 millimeter. So let me see. Is this in me? This is in meters. So I want that 0.00027. Is that 0.00027? All right, that's fine. Oops. Yeah. You know, to make sure I'm at least 30, I'll start at 0.00028. Uh, and here we are. So let me try that out. You can see it's taking much more time I might edit out parts that I'm kind of just waiting. Yeah, let's see how long this takes. But the point being, 3D meshing will take much more time, and this is an unstructured mesh. So in general, this actually looks like, kind of interestingly structured, but in reality, it's not really that structured. uh, I think I'm actually not supposed to be doing body sizing. I'm supposed to be doing, uh, what do you call it? I need to change this. It's not just element size, because right now there's two separate bodies with two separate meshes. I need to do a body of influence. So this is taking a while. Well, we'll see. It's probably because, uh, yeah, we'll see. I will let you guys know, and I'll be back when this is done. Alright, so we're back after probably, took like another 2 minutes or so, but I did have to change it, so I had my body sizing wrong. It was under element size, but you want body of influence. And so that tells that this smaller body inside is going to influence this bigger body. So you should make sure that when you click this mesh button, it shows the complete mesh. And so I should be able to, I don't think I suppressed this, but I can hide it, and I simply have a mesh that has the influence from this body sizing. So I set that element size, yeah, from this body onto this body. And so this is my main mesh, and my inflation layers got applied. So when I see my front view, you can see right here. So basically, there's 15 layers of a growth rate of 1.2 starting at that first layer height. So this first layer height corresponds to y plus of 3, and it grows up. And this volume, someone once told me that in general, whenever cell jumps to the volume of one cell next to the next cell should be no more than something like twice. Or in general, you don't want the volume of one cell to the next cell to be huge. You don't want that difference to be huge. If this cell was, let's say, 50 times bigger, there were times that I had a bunch of edge sizings in a meshing, and the difference in volume is like 50 to 100, and you get some weird pressure gradients, and shit just does not work out well. But in this case, it probably works fine. Like, this volume change is not that big. Even in this, it's not that big. I think this, looks respectable. Um, you can see actually my mesh size is 3 million now. So you can see how this grows very quickly. Right now it doesn't look that bad, but it's because it's in 3D. So imagine whatever you see right here, but multiplied by some unit depth. And if you want to cut it in half, uh, oops. Yeah, if you want to see how it is, you can use this section plane, and you literally draw like this slice, and boom, you can now look at it as a slice. And so here you can make sure that, alright, even halfway through in the 3D mesh, looks generally right, looks right, inflation layer is proper. All of this weird mumbo jumbo, no idea why that happens, but generally that's just, I think it's because you're taking some 3D slice. So when I unclick that, boom, I see the edge again. So I think this looks generally ready to go. I am going to have to make sure my inlet. Ooh, so now these are 3D. So I need to choose the surface. I will choose, honestly, everything. Oh shoot, actually wait. Because this is 3D, so you kind of got to think about it. So I mean, when it comes to 3D, it really just sets your, these are just boundary layers. So I think this actually should be okay. Because flow into the screen here or flow here doesn't matter. Yeah, I think for, yeah, actually this would probably be better because if I set these parts to walls, it might it might mess up the fact that I'm going from a velocity inlet to this boundary condition being 0. It might be a little bit weird. Don't know. This is my first time trying it. Outlet, airfoil. So actually, I could create walls. Then you'll see how it is. Yeah, sure. You know, actually, I'm gonna change this. Uh, actually, sure. I'll change it. I'll change it. And in the case this doesn't work, I'm gonna simply set these walls to be a velocity inlet. Because if I set these walls to be a velocity inlet or a pressure far field, it basically acts like the walls an infinitely far distance. That's the exact same value as the inlet. So inlet, outlet, airfoil walls. Dang, I should have chosen a dimension that looks more, I don't know, rectangular or like this is a very slim rectangle. Uh, and yeah, actually, I'm only gonna do like 4 degrees angle of attack, and that's not gonna make. I only made these far away because I was afraid that if I try some angle of attack that, it might hit the wall or something like that. And if I was to set these as velocity inlets and I had it going up this way, that would give some like wrong values. But I think this works. I'll save now. I don't think you have to save here whenever you do stuff. I think you can just close out and update the mesh. Could be wrong though. Takes a while. This thing is 3 million cells, so unfortunately it's not going to be the fastest simulation. And I have to update this. This update takes forever, relatively. But right now it's the quarantine, so hopefully, uh, this I'll look back at this one day and be like, wow, I was doing CFD in quarantine time. I'm also done with classes, so I won't be. I'll be in my PhD program in a few months, but until then, I'm kind of just chilling and trying to feel not super bored. Alright, this is taking some time. Boom, finally. Oh, not even done. There we go. Yes. So I'm using 10 processes in parallel. Yeah, that's fine. The more in parallel, the better. Parallel computing is like a whole field of stuff. Basically, it kind of divides your thing into your whole fluid domain into like 10 parts. It kind of basically breaks it up into 10 partitions and it solves each one in parallel simultaneously and it puts your solution together. It kind of, yeah, it takes it apart, solves it in parallel instead of solving it, one by one by one. If you guys know video rendering, if you guys have seen that, then you guys probably know the difference between serial and parallel. So, here I have my mesh. I should only have one fluid zone. If you have two, something's wrong. Oh, if you have two, you probably didn't delete your connections. You have to or contacts. You have to delete your contacts because that says like because I had two bodies and you have to get rid. It has to think that there's only one body, so you have to delete the contact. Like literally delete all of it. I am gonna use not splatter Mars, remember, because it uses, I will use K-Epsilon. You can look up different models. Generally, people use realizable. I know enhanced wall treatment works well on all y plus values because it has blending functions, so it works on everything. I forget the differences. I should have looked that up before made this video, but enhanced wall treatment should work because it has blending wall functions. Realizable K epsilon, I believe works the best. Air, solid, fine. Boundary conditions, velocity inlet. So I think I had it like 44 point. Yeah, I ran some basic ones. 0.32, 1%. This is 2 meters now. Turbulent length. Oh shoot, actually, this turbulent length scale is I believe it is the size of the eddy currents. And there is some empirical, general relationship, uh, but just to say it's low turbulent, I think, if I recall correctly, it might have been zero point 0.3 times chord length. So if it is that, I will make my size of my eddy currents 0 0.3 times 2, 0 0.6 meters. And I will have this in the x direction. Let's see if the walls work. I'm going to set these as walls. Might not work super well, but let's see. Reference values. So now force coefficients use reference areas, density, velocity. And so remember, lift or drag, it really doesn't matter. They both are the same non-dimensional terms. It's the force, density, velocity, area. And this area is your chord length or reference area. And so I believe for airfoils, it is still the chord length. It's still m squared, but it's chord length. So it doesn't even use this length. So like I could set this as like 50 million. And I can show you. It really doesn't matter. I'll do this from inlet. So 1.225 density. Simple is fine. These should be higher orders, but I will leave it as first order for now. I will create a force report. I want to see the drag. This is something I've never actually done myself yet. Force coefficient. Yes. I only have one inlet. I don't want to set any convergence. This would stop it if it ever reaches these values. And these values are pretty crap for convergence criteria. Initialize. If this does not detect divergence, we should be okay. Please. Sometimes this is actually where, when I had that old mesh, this is where it fell apart. This is where uh, the shit broke. It basically said divergence detected. I don't know how this hybrid initialization gives some good initial guess. I don't know how. You can manually set it to be, so if in StarCCM I said I want everything to start off at 0. In that case it might take a while to reach, but that's a decent guess. But so yeah, you could manually set it to some value, but hybridization does fine. Alright, let's see if this diverges instantly. And we will look at the velocity profiles. What we'll eventually do is we'll create a plane. We'll kind of split it up like how I split up the mesh to see how the contour looks inside. Wow, there's 3 million cells. It's going to take a while. I pray to God this doesn't take too long. Well, I will be back. Or I want to see does this even like do 10? Oh gosh, finally. This might take a while. So let this be a warning. to whenever you're doing 3D simulations, uh, yeah, like honestly, you could have set these wall. I could have set those walls much smaller. Boom, 10. Gosh, this is gonna take forever. All right, I'll be back. Maybe an hour. No idea. You know, in the real world simulations, some of the best simulations will take forever. NASA has this video. Dude, I gotta show that video. Alright, so looks like I ran it for about 490. I could have ran it for longer, but just looking at the drag, um, it looks like the most important parts are resolved. So this is 3D, so the way if you want to see a slice, you kind of have to create a surface, plane, and knowing that my thing was extruded point 0.5, I'm gonna make, where are these X? So I want to try do a whole plane. Actually, I should have remembered like where it was. Darn it. I don't remember how I dimensioned it, but I might have made it something like, I really don't know. Hopefully this is good enough. Don't really remember. Uh, and my Z, this is halfway. My Z was extruded 0.5, so this is halfway. I think this might be it, so create. And I can see it by, why is this taking forever? So it's kind of lagging right now. I simply wanted to show the walls. I probably should have just clicked walls. Uh, yeah. So these are the walls, and I want to show halfway in the middle. So if I did this right, yep, looks like that plane is halfway in the middle. About. So like this is the plane, I want to show it. Graphics, create a contour plot on top of this plane. So on the surface, I have to collect that new plane. And moment of truth, boom. This looks decent actually at first glance. Wow, I'm impressed by myself. Let's look at the velocity magnitude. Boom, this looks pretty good. And so actually, take a look. You see the walls. These are wall values. So I have 0 values because, you know, at a wall, there should be none. So you see here that it is 0, but it doesn't really affect here. And it actually could be, but it shouldn't be. And so, I don't know why there's some glare. There's like, boom. So if I want to angle it a little bit, wow, this looks pretty good. I want to make this banded. Like this. Oh, you see, actually, there kind of is some wall effects. This should not be, because right now it says that, why does it, that this happens sometimes. Right now, this value is somewhere between 42, 40, which is kind of, and if you want to make it more detailed, you can color map options. Let me make this 30. God damn it. So actually, it might not be fully converged because this total outside should not have a difference. And right now there still is a difference. And drag wise, I think drag is lower than expected. Yeah, this is lower. So at this Reynolds number, if we recall, do I have it somewhere? Or I believe it should be 0.008 because this is still technically a 2D model. So at 0 degrees angle of attack, yeah, it should be 0.008. And I can just see the lift too. I mean, lift right now, yeah, that's basically 0 because it's symmetric. I could let it converge more, but I think this wrong value of CD, I mean, it could be from a multiple of things. Could be the model itself, could be my reference values. So, like one thing I can show you is if I change this to even say 10, my you see the coefficient didn't change. So this length is, it doesn't even use this length right now. It really just uses area, which is chord length, I believe. Uh, what if I change this to 1? So you can see if I change this to 1, it doubles, basically, yeah. Nope, this should be right. Trying to think to velocity inlets such that you don't see this might make a difference. And simply because it's 3D, the room for error is just way bigger. You know, in 2D, there's a whole less dimension of error. So actually, I changed this to match that that CFD case. What do they use? Intensity. Boom, turbulent intensity of 0.052. Viscosity ratio, they use is that right? 0.009. Yeah, that's basically 0. That's almost, yeah. So if I change this, let's see how this changes. I don't actually expect it to change much. So right now, basically, the CD is an under prediction. That could be because of simply the model itself, but I'll be back. So here's after I let it run for a couple hundred iterations, maybe like 20 minutes. I just did some work, and the drag after changing it from wall condition, or after changing the walls from a wall to velocity inlet, you can see the drag dropped not significantly, but it went from 0.006 to 0.00, 4 or something like that, 0.03839 maybe. And that's basically, that shows you the effects of wall effects. So if I had it much farther away, those walls would not have had an effect on the drag. But from right now, it looks like my drag is an under prediction. I don't know why. My lift is pretty good, basically 0. To show this more, I want to start doing, and so if I look at my contour too, like close to the airfoil, this looks pretty decent, to be honest. This stuff should not be a different color. That's probably due to convergence, and it probably will go away eventually once if I let it run more. Like you can see, it has room to go more down, but overall this actually looks kind of decent. Uh, so I'm gonna change the inlet. I'm gonna make all of my velocity, and this is actually where I'm gonna keep my velocity inlets, uh, my walls as a velocity inlet, because if I was to do a angle of attack with a different angle of attack, or if I was to keep these as walls and I just made this come at an angle, it would hit the wall and want to come out. So uh, to do an angle of attack, it's best to keep the walls as either a velocity inlet or go back and remesh it as an angled airfoil, because in actual wind tunnels, as I mentioned, the velocity usually stays constant and this changes. Um, to kind of cheat, I in those other videos I simply said it was the other way around and it didn't matter, but right now it's just getting a bit more complex, so I will change my velocity inlets to here cosine. I pray this works. Yep. Alright, so I basically changed the boundary conditions of here. This is still a velocity outlet. Yep, I think this should continue to work. Alright, so we're finally back. I let it run for a good, I don't know, 20, 30 minutes. I fixed what was wrong with the reference value. So I was just Googling somewhere. Shoot, where it was. But basically, uh, the reference value area is the top view. So something I just read and it works out. And I was noticing it was kind of off by a factor of 2. Um, and I just read that it's the top view, not the front of view of an airfoil is how it looks from the top. So from the top, it is the chord length. So let me. So from the top, it's actually the chord length times the span. So not the front. If it was, I know for cars, I believe usually they do the front, which is kind of like the span times the height or thickness. But for airfoils and wings, generally it's that top view. So in this case, chord length times span. So that, in my case, actually comes out to be 1, which is the exact reference area I had in my 1D dimension, where I had a chord length of 1 and a depth of default 1. So once I change my, uh, what do you call it? My reference value to be 1, I get exactly, my CL is right, is 0.459, comparing that to, uh, the CL of a 2D NACA is 0.43. That's, what is that percent error? That's like 0.02. What is that, like 5%? Something like that. Something like 5%. Pretty acceptable. The drag, a little bit more off. So I have 0.011 compared to 0.008. And as I mentioned before, this is very well documented. Almost all turbulence models over predicts uh, the drag. It partly could be because in this I have my walls as velocity inlets, and in a normal wind tunnel, like whatever how this was taken, uh, they have walls, so there's maybe teeny tiny wall effects. There's a plethora of possible reasons why, but generally, so let that be a lesson learned for me and for other people. Reference values for airfoils is chord length multiplied by span. Um, so in this case, I have my contours, but it looks good, except these blobs. So if it wasn't for these two things, this would look pretty solid. Not perfect. I'd expect it to look a little bit different, but that's also because of the domain. So hopefully you guys now know how to do this. There's a lot of other things. If you guys want to add path lines, you guys can do a 3D. So like something cool. Shoot, can I do this? Okay, let's see if I do this in the first try. I could do line arrows, so I'm gonna make this a 3D show of how it would look. Oh, and actually one thing with contours too is it's cool to do 3D contours on maybe the airfoil. I don't know why it does that. Sometimes when if you go straight into velocity contour, it doesn't work. It shows like all blue, which is not actually how it is. You do pressure first, and then it works. So pressure, you can see red is high, and you expect a lower pressure on the top because there's now a lift force. So lower pressure, slightly, or yeah, higher pressure, and there's more blue at the top. Blue is negative, so it's an upward lifting force, which is correct. So this is the contour of a 3D airfoil. Uh, yeah, to show those particles. Now this takes actually some time. I think it's generally actually in path lines. Uh, so it's kind of like this is how, what color you want your arrows. Release from inlet, step size, 5,000 steps. This might take a while. Oh, yikes. So these arrows way too big. I need to like make this point maybe 0.01. I'll make all of these 0.01 because this I know from first-hand that these baseline arrows are hella whack. I always gotta play with them. Okay, so oh no shit. I think they just crashed. Wow. So since visualizing it in my Fluent, if for some reason it's crashing my Fluent, I actually want to try to show it in CFD Post. So on the results, it defaultly uses this software called CFD Post. It should have your data loaded up already as long as you save your stuff. So I can choose what gets shown and what doesn't. Uh, so I want to show this is my airfoil basically. There should be a way to like hide some of these walls. Like this might work actually. Like maybe it's not. It should be able to work. Uh oh, this is probably under wireframe or something. Oh, wireframe. Boom. There we go. So I want to show the airflow around it. So I need to define I believe it has to be a plane one. So it will be in my YZ plane. Uh, X. Put this. Yes, and it will be sampled. So I'm gonna make this somewhere. Yeah, -1 is good. Y will be 0.25. I'm just gonna make these all 0.25s. I think this should work. This says how many. It's kind of like, yeah, it basically says how many points can come out of this. I think this should work. So I create a plane. Ooh, that's a small plane. Let me make this bigger. For some reason, it is not in line with it. Do I know why? No idea. Yeah, that can't be right. Why is it off-centered? I have no idea. But let's see if it works. I'm gonna try to insert a streamline. I'm gonna start from my plane 1. I'm gonna have 100 points. Show velocity. So it's generating. Boom. Kinda cool. I can make this should be able to, I can have more points, I can have less points. I can add. Now where do I do to add symbols? Nope, it's not it. It's not a tube. Don't want to show a tube, that's kinda ugly. I can make this width smaller. I should be able to make it pulse, actually. Could be on the particle track. There's actually, oh, there's other ways you can make a vector. You can show a vector on the streamlines. Yeah, so right now, and I need to make the size smaller. So you guys can see here, it's showing the actual lines. I will do arrowhead 3D. Boom. So this is kind of cool. You can actually show, maybe you want to take a picture, I don't know how you want to take a picture, and it shows the velocity of a 3D wing in 3D. Yep, you can hide your plane. Why is this only showing half? No idea. Maybe let me define my plane differently. So I want to have it more in this. Is it the Y? Let's see if this works. Yep, that kind of worked. To my suspicion. Kind of works. You can show it shows 3D arrows. For the streamline, I believe I can make it pulse. It might be on the particle track. But this is something you guys can play around with. So this is just some basic post processing. Uh, there should be a way. You can make a volume render. That's pretty cool too. I'm trying to remember if there's a way to make it pulse. That might just be in ANSYS Fluent. So actually, that might be right. In CFD post, you might have to save transient to make it pulse, but I don't remember. But hopefully this fits within an hour. Hopefully that showed you guys how to run simulation. You guys, I don't know if I showed you, but when I redid this with the corrected reference values, I get the correct amount of drag, the correct amount of lift at 0, and 4 degrees angle of attack. That matches the 2D model. And it should match the 2D model because this is essentially a 2D model. If you guys want to do 3D model like an actual wing, that's probably some lofted shape from SolidWorks, I can show that. But hopefully this helps some of you guys.